Okay, guys, can you guys hear me? Can you guys hear me? You can give me a signal, but you guys can hear me. So we're actually using the Zoom application. You have two ways to communicate with me. One is you can just basically unmute yourself. You can talk, I'll be able to hear you. That's like the best way. Or alternatively, if you're a little bit shy, which I highly doubt, you'll be able to use the chat function, talk to me. So do you guys know how to use the chat? You go to the console. In the console, there will be a chat option. You click that chat option, you'll be able to see my name and the chat. Okay, perfect. I see you guys. Let's give it maybe 1 more minute while we're receiving more students. It's the first lecture. We always have some students have some technical issues here and there. So we might be delayed for 1 or 2 minutes. Okay, so 1 more minute, we'll be able to get started. All right, it's 7:02, so let's get started. Okay, we have some students that are coming. It's okay, we can get started. So welcome to our knowledge-based lectures. So we just finished our boot camp for 2023, MC10 and MC12. So a little bit different from the boot camp lectures. For our knowledge-based lectures, we're more, go to the details, give you guys all the dynamic for all the technologies. So in our session, we have 8 sessions in total. Pretty much covered everything from algebra, geometry, counting probability, and number theory. So for our current session is session 4, is the circle and coordinate geometry. So circle, we know that, right? It's kind of like pretty much all the technologies from 2D geometry will be applied to the circle. You'll be use the circle as a background, try to solve a lot of complicated problems. And also coordinate geometry. Coordinate geometry is basically using the algebra technology try to solve a geometry problem. It's kind of like a liaison between the pure geometry and pure algebra. So basically in our session, 10 lectures, we're going to be covering these two topics, circle and the coordinate geometry. Okay, so let's get started with the first part, the circle. All right, so talking about the circle, this is actually an extension for our session 3. If some of you guys have been to our session 3, we're talking about triangles, quadrilaterals, polygons, so on and so forth. So this is kind of like an extension. We're going to use all the technologies we have learned from session 3, try to apply them one more time on the circle-related problems. Okay? And for the new student, here's a quick kind of an introduction. For our knowledge-based lectures, we want to basically give you guys two very important things. One is all the concepts, very grounded into detailed concepts with all the explanations, all the summaries for the topic. And the second one is that we're going to give you guys to a kind of like a walkthrough about all the classical, typical problems that you might be seeing in this part. So we're not always go for the problems, do the problems one after another, or just focus on the concepts. It's kind of like a combination. You need to understand all the knowledge base. And then taking from there, let's try to summarize the most important, the classical problems. And then moving forward, try to give you guys a lot of like interesting problems, and then you'll be able to get a hang of it. Try to use the technologies, try to solve real problems. And for the problems we're going to be giving you guys, it's pretty much scattered all over the places. You could be seeing some American math competitions, some Canadian math competitions, or some Asia, some Eastern Europe. We're trying to pick as many problems as possible, give you guys kind of like overall rounded introduction about all the technologies for this part. So don't be shy. If you have any questions during the process, just let me know. You can always unmute yourself, ask a question, or alternatively, you can chat with me. I will still have a lot of interactions with you guys. So I'm going to stop and ask you guys, what do you think? You guys tell me what to do, and then we'll be able to move forward. This is like the overall strategy for our lecture. Okay, if everything is good, let's fly to our first section. We're going to go to our circle part. Okay, this is our lecture number 1. So in the first lecture, we're going to talk something about the circle basics. Not something too complicated, too fancy. We just go for some basics. Okay. So one more thing I would like to say is that to come to our lecture, we have an assumption that you already have some basic knowledge about the concepts. You're not like, this is my first time ever learning circle. In that case, you might go to another session. So in our session, we're going to be more kind of like based on the assumption that you already know something. We just help you guys to summarize whatever that you have to know. All right. Okay, the first part, we're going to talk something about the circle basics. So there are so many concepts for the circles, so we have to summarize them one by one. The first one is some definition. So what is a circle? The circle is actually a very simple closed shape, right? It's a simple closed shape. So how to define a circle? The circle can be defined a set of all points in the plane that are at a given distance from a given point, aka the center. Right? I think this is a very understandable definition talking about a circle. A circle is a closed shape. So what are the points in the circle? It's a set of all the points in the plane that are at a given distance from a given point. And that given point is called a center. This is quite a brief, understandable definition, right? And then after you know the definition, we're going to go to the second part. Let's try to summarize some basic terminologies. So what are the basic terminologies that we're going to be using in the circle? So let's have a quick look at it. I'm pretty sure everyone knows that already. We just want to take this opportunity to have some quick summary. So let's say I have 2 points in my circle, A and B. So A and B, like the kind of like the round part between A and B, this is what we call an arc, right? Okay, so the distance between A and B, we call this is a chord, right? I assume, guys, you already know what I'm talking about, right? The chord, the arc. And what else? So let's say I have a line which is outside my circle. I'm going to use the color green. If the line goes like this, it cuts the circle into 2 points. So I'm going to give this line a name. This is a secant, right? The secant cuts the circle into 2 points. Or if the line is exactly cutting my circle at 1 point, not 2 points, here, exactly 1 point. Okay, I'm going to give a name to this line. That is a tangent, right? And also for the specific intersection point, I give a name, tangent foot. Is it understandable? This is something quite understandable, right? So a secant and a tangent, the only difference is the secant cut the circle into 2 points, while the tangent just go for 1 point. So secant goes for 2 points, tangent goes for 1 point. Of course, we know that tangent is only a specific scenario of secant. Secant is more generic, right? Well, tangent is kind of like when the secant is moving all the way until these 2 points degraded into 1, and then a secant goes to a tangent. This is quite understandable stuff, right? What else? Let's say I have a circle center. From the circle center, I want to make, kind of like this, right? This is my O, and these are two R. So this is actually generating a sector, right? We call this as a sector. Okay, I think this is quite understandable, right? All right, from the sector, we would be able to find an angle. Let's say there's an angle here, theta. The angle, one of the vertex is the center, and it has two radius, right? Use the two radius as the two sides of this angle. I give a name. Theta is actually what? A central angle. Central angle has one of the vertex at the circle center, and there's two rays as well of kind of like a two radius. So this is a center circle. Okay, but what if I have another circle? I'm gonna say this. I have another angle. It's basically like this. So one of the vertex is actually on the circle. Well, they have two rays as one of the two chords. So this is what we gave name. Let's say phi. 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 This is called inscribed angle. Right? So we have two angles. One is the center angle. The other one is the inscribed angle. So is there any relationship between these two angles? Of course, we know that as long as they're facing the same chord, or the same arc, it doesn't matter, right? I have always my center angle is twice of my inscribed angle. So far, so good? My center angle is always twice of my inscribed angle, provided they are facing the same arc or the same chord, whatever. So far, so good? I think these are very basic under stuff, right? It's kind of like 101 stuff. All right. So after having all those basic terminologies, so maybe I'm going to give you some kind of like very basic properties as well. So let's have a quick look at it. If I have a circle, these are also very basic stuff. Everyone knows that. Okay, let's say I have this. This is my center O, right? So this is my R, and this is my theta. Okay, I have a center angle, name is theta. So talking about my area, how to determine the area of my sector? Who can tell me? How to determine the area of my center, of my sector? These are very basic stuff. Area of my sector.
Is it pi r squared times theta over 360?
Is it right? That's very brilliant, yeah? Pi r squared, that's my real circle's area, and then times theta over 360 degrees, right? Or maybe most of the time we like to use the radian, right? So that's going to be like pi r squared theta over 2 pi, right? This is more like in our math. We do not really use the angle a lot. We like to use the radian. This is something quite understandable, right? Then what about how can I determine another very easy stuff? How can I determine the circumference of my sector? Okay, circumference. Circumference means what? The entire parameter, right? Parameter of this entire thing. How can I determine this? This is also very easy. What is the what is circumference for this entire sector? What is that? Who can tell me? How to determine the kind of like a parameter of this entire sector?
Pi 2 pi r times theta over 360 plus 2r.
2 pi, right?
Oh,
Plus
yeah,
2r.
2 pi.
Yeah, this is quite understandable, right? These are basic stuff, right? You need to understand how to determine the area for a sector and also the circumference of a sector. I think this is something quite understandable, right? Nothing complicated, nothing very strange. So these are kind of like the basic terminologies, basic stuff you have to know talking about the circle. I assume already you guys know that from day one. All right, if all good, let's move to the second part. Let's talk about some important properties in a circle. Okay, I'm talking about some basic property. I'm not talking about some very complicated rules that we will talk about in our next lecture. It's okay, just some basic properties. First one, we're going to talk something the chords of a circle theorem. So let's say I got a circle. In the circle, I have a chord. Okay. If I want to make the bisection of the chord, a bisection of the chord. Okay, this is my bisection. Bisection means what? I have a line which is perpendicular to my chord and also cut my chord into two equal parts. Okay, so I'll say the perpendicular bisection of a chord must passes through the center of the circle. Right? This is like a given, quite intuitive, right? If I have a chord within the circle, and then I make a bisection, the perpendicular bisection, a line which cuts the circle, the chord into two parts, and also perpendicular to the chord, that line is going to pass the center of my circle. That is something quite understand, right? Nothing complicated, nothing special. All right. So moving forward, I think there's another thing I like to say. In the same circle, the same chord in length. The same chord in length means that they're going to facing the same arc in length. Is it right? So I'm going to give you this. In my circle, oops. In my circle, if I have two chords, they are the same length. Here, okay, they're the same length. So that being said, let's say, I'll give a name AB, CD, right? If AB chord is the same as CD chord, so that being said, AB arc is the same as CD arc, right? This is kind of like a easy peasy stuff. Those two arcs are the same. Yeah, and also they must be facing the same central angle and the same inscribed angle. Right? Let's say I want to find out what is my central angle. I'm going to use the color maybe black. So they are facing two different central angles, and these two central angles must be the same. Right? As long as the two chords are the same, or the two arcs are the same. Basically, the two central angles are the same. And also, they are facing the same, and use different color, maybe yellow. They're going to be facing the same inscribed angle. Is that right? So these two inscribed angle are also the same. So that being said, in the same circle, as long as the chord is the same, so the arc are the same, the central angle, the inscribed angle are the same. This is quite intuitive, right? And also, this is actually a sufficient and a necessary condition. As long as you have two inscribed angles, they're the same. So they will be facing the same chord, the same arc, and the same central angle. So this is, everyone is necessary and sufficient condition, right? I think this is quite understandable. But this is one thing you need to remember is in order to make it work, they must be in the same circle, right? It's always in the same circle. You have the same arc, same length, same chord, same central angle, same inscribed angle. They're all the same thing. But as long as you go to different chords, for like different circles, unfortunately, this does not be respected, right? And generally speaking, a larger chord is always indicating a larger arc and larger angles. This is quite understandable, right? Generally speaking, if you have a larger chord, it's going to facing a larger arc, a larger angle. This is something quite understandable. So far, so good? All right. Trust me, this is like so easy stuff, right? But using this easy stuff, we can do some very interesting problems. You know what? Let's go for one problem. Just try to see how we can use this basic stuff. Try to solve it. Okay, it's time for problem. We always want to give you some problems, some real questions back and forth. Then you have an idea how this one works. So let's go for a problem that comes from 2001 AMY American Invitational Math Exam 1, question number 13. Even though, oh my God, this is question number 13. You guys know that AMY only have like 15 problems. This is kind of like last 2-3 problems. But trust me, even though it looks like so crazy, but the solution process is fairly understandable. Let's have a quick look. What's going to happen? The problem says in a certain circle, the chord of a d-degree arc. Okay, I'm going to highlight it. D-degree arc, d-degree arc, because the arc has a degree, right? A chord of a d-degree arc is 22 centimeters long. Okay. The chord of a 2d-degree arc is 20 centimeters long. 20 centimeters longer than the chord of a 3D arc. Okay. So where d is lesser than 120, the length of the chord of a 3D-degree arc is minus m plus or under root n centimeters, where m and are positive integers. Find the value for m plus n. I don't know if you guys are familiar with this. This is a typical AMY way that to ask you a problem. Because AMY is always, AMY is actually, this is not a multiple choice, but you have like the answers, right? It's going to be a computer-based problem, like a computer-based, like their answer sheet. So it's always a number from 0 to 999, right? As long as you have such a weird answer, the computer can't read. So they always want to kind of like make it into some simplified forms and then try to add those numbers together. Then you will be able to generate a number from 0 to 999. This is like a typical way that AMY asks a question. But long story short, the question always want to ask you, what is the length of my chord facing a 3D degree? Well, this problem, as long as you read it, did you find anything a little bit special? So I'm going to write it here. You see, a D degree. The chord is 22 centimeters. A 2D degree chord. Remove, okay, a 2D degree and a 3D degree. The question says the 2D degree chord is what? 20 centimeters longer than the chord of 3D degrees. So 2D degrees, this chord is longer than the 3D degree chord. The difference is 20 centimeters. Just by reading this, did you find something a little bit special? a little bit strange, if I may say. Let's have some discussion. I want you guys to all get involved. Okay, not like our bootcamp lectures. We have so many students. Our kind of like knowledge-based lectures is very, our volume is very, our like, what should I say? Class scale is very small. Everyone get an opportunity to talk with me. Who can tell me, as long as you're reading this, did you find anything special? Anything doesn't make sense? Who can tell me?
The smaller angle has a larger arc.
Is that right? Yeah, I think that's a brilliant observation. Because normally we say a larger angle or larger arc has a larger chord, right? That's basically what we see here. Generally speaking, larger chord, larger arc, larger angles. But now the question says a 2D degree arc facing the chord is actually even longer than the 3D degree arc. Is it gonna happen? Why? I'm gonna give you let's have a quick discussion. Let's say, generally speaking, you see here, right? So the arc, this is my here, 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 here. You know, if you have a longer chord, you're basically facing a larger arc, right? A shorter chord facing a shorter arc. But now, why a 2D degree arc actually facing an even longer chord than the 3D degree arc? What's going to happen? In what kind of circumstances that would happen? Apparently, that's not the general speaking terminology, right? Can you think about it? Why, in what kind of circumstances that might happen? So this is one of the tricky part for this problem. And why this problem go to question number 13? Because in the circle, talking about the arc, we actually have two kinds of arcs. One is what we call a minor arc. One is what we call a major arc. Did you guys notice? Minor arc and major arc. Do you guys notice? Yes or no? Have you heard about the terminology? Minor arc is actually the arc which is lesser than the semicircle. Major arc is the arc which is larger than the semicircle. I'll give you an example. Let's say, still going to give you a circle. In the circle, let's say I have 2 points, A and B. Most of the time when we talk about arc AB, it's always the minor arc. The one goes like this. This is my AB arc, right? Without specific explanation, that's basically what we want. But alternatively, we also have such an arc. This is also AB arc, right? Arc, the definition is actually, I find 2 points in the circle, and then, the part of the circle between these 2 points will be considered as an arc. So, but of course, AB arc, the red one is lesser than the semicircle, while the green one is greater than the semicircle, right? So this is actually what we call a minor arc. This is what we call a major arc. Okay, they are both facing the same chord AB, but you have 2 different arcs. Okay, so maybe in that case, let's try to think about it. If we talk about the major arc, you see, major arc AB is the green one, and AB is my chord. What if I find another arc? This is AC. My major arc is here. My AC arc is actually bigger. If we're talking about the major one, my AC arc is bigger than my AB arc. However, my AC chord is actually smaller than my AB chord. Make sense? So that's the reason why I'm saying, generally speaking, larger arc, larger chord, larger angle, these are all focused on the minor arc. As long as you have minor arc and major arc all blended together, it's not always guaranteed. You might have a larger arc, but facing a smaller chord. And I think this is basically the rationale for this problem. You're looking at 2D degree arc. It's actually 20 centimeters longer than the 3D degree arc. And that being said, we must be looking at some major arcs in such a problem. Does it make sense? Okay, but the million-dollar question is, how can I find out all those arcs? You have D, you have 2D, you have 3D. How to make the entire thing more straightforward? This is the most challenging part for this problem. And why this is question number 13, you have to do a little bit construction. You have to create a graph which has 1D, 2D, 3D, and then you have all the arcs there to represent all the relationship that is given by the problem. So this is the most challenging part. I'm going to give you the answer. We can have a quick look at it, and you will find it's very beautiful for the solution. Oops, not that one. It's here, image here. It's going to be here. Look at that. This is the solution for this problem. But like I said, you need a lot of construction to make it work. Let's have a look at it. It doesn't hurt to have a look at it. Now, we're actually creating such a shape. Okay, in the shape, you have, this is 1D, 2D, 3Ds, right? Okay, so let's have a look at it. The question says what? The first one, as long as you have a D degree arc, the facing chord will be 22 centimeters. Okay, this is going to be 22 centimeters, right? This is going to be 22 centimeters. This is going to be 22 centimeters. Quite understandable, right? I'm going to highlight it. 22. It's going to be 22. This is going to be 22. This is understandable. But now the question says a 2D degree arc facing chord is what? Is 20 centimeters longer than the 3D degree arc facing chord. So what is my 3D? My 3D degree arc is already here. This must be a major arc, right? So what is the chord that they're facing? They're facing here. This is the little one, CD, right? The big major arc, almost like entire circle, facing a tiny chord. So that one is actually 20 centimeters lesser than the 2D degree arc. I'm going to say this is X. So the 2D degree arc is going to be what? X plus 20. So what is my 2D? This is my 2D degree arc. They are facing, this is also a major arc. So this is actually facing one of this, right? This is the 2D degree arc, major arc facing chord. And this is what? X plus 20. This is only for one side, and try to use the symmetric property. This is also on the other side. X plus 20. So far, so good. Can I have some feedbacks? Do you guys follow me? Yes or no? Hey guys, you guys are there? Yes or no? Can I have some feedbacks? If you're with me?
Can you explain why it's X plus 20 again?
X plus 20? Because the question says here, the 2D degree arc is 20 centimeters longer than the chord of 3D arc. This is given by the problem. So 3D degree, I'm going to give the color. 3D degree color is X. 2D degree color is green, X plus 20. And D degree is just 22. 3 colors. Green is 2D, blue is 3D, and red is 1D. Do you guys follow me for this? The other students, Anthony, Toki, is it all good?
Yeah.
Any? Okay, yeah. Any question? If you don't understand, let me know, because I have no idea where you stand. Our lectures, our complicity is always adjusted based on your feedback. Because I have a baseline, right? I always start with my baseline. But the more you're telling me, okay, Alex, this is too easy. Okay, I'm going to give you more and more complicated problem. Or you're telling me this is too hard, I can't even understand. I'm going to reduce the complexity. But if you never talk, I can't read your mind, right? You have to let me know where you stand, and then I'll be able to adjust my complexity levels. All right. So now it looks like the question is asking for what? The length of the chord of a 3D is blah, blah, blah. So you need to determine X. Who can tell me? How can I determine X? How can I determine X? I need an equation, right? I need an equation to determine X. What is the most straightforward equation that can help me determine X? Give you 1 minute. Think about it. Okay. How can I use some easy peasy equation to figure out how to determine the value of X? Who can tell me? Because I only have one variable, right? To solve this one variable thing, I just need one equation. How can I just use one equation to solve this one variable? Who can tell me? You see the red, the blue, the 2 greens, it's kind of like, you know what? In the quadrilateral, right? If I highlighted this, who can tell me what kind of technologies I can utilize try to solve this? Everything is actually squeezed in the quadrilateral, right? Can I do anything for this quadrilateral to find out a relationship? I just need one relationship. Nothing too complicated, nothing too flowery. One will be good. You see 4 sizes. 3 are red, 1 is blue, and you see 2 diagonals. What kind of theorem you think about it? You can solve this. This is not a normal quadrilateral. This is a cyclic quadrilateral, right? Because A, B, C, D, they're all on the same circle. What is kind of like a big kick, kind of like big sparkling? What should I do? Who can tell me? Who can tell me? Who can tell me? For cyclic quadrilateral, what is the most important property? Ptolemy, right? Ptolemy theory, right? Any kind of like quadrilateral, as long as you're cyclic, you're gonna go for the Ptolemy theory. Did you guys notice Ptolemy theory? Yes or no?
No.
Okay, so you never heard about it. Okay, in that case, I'll give you a quick explanation. Yeah, Ptolemy theory is especially for inscribed circle. As long as you have an inscribed, like the inscribed quadrilateral, in any kind of inscribed quadrilateral, you have such a relationship. AB times CD plus AD times BC equals to AC times BD. AB, DC, the opposite two sizes. AD, BC, the opposite two sizes. If you have two opposite sizes, you multiply them, and add them together, it's going to be equal to the two diagonals product. So this is AB times CD, the two black one, AD times BC, the two yellow one, equals to AC times BD, the two green one. This is a very important theorem. Remember it. It works for all the cyclic quadrilaterals. Okay? This is very important. Even AMC 10 tested every single time. So you guys need to know this. Okay? We're going to talk about it in our later lectures. I assume you guys already know that, but if not, it's okay. I'm just going to give you the explanation. That's the Ptolemy theorem. Okay. With that, can you, if I just show you this, let's say, if you don't know this before, it doesn't matter. I'm just going to show you this. With this, can you find an equation for my x? I'm just going to use it here. Can you tell me the equation? Please post your answers into the group chat. I would like to see where you apply this technology right away. 1 minute. You just use whatever I just told you. Try to find out an equation for x. Please post your answers into the group chat. Yes, yeah, you need to use it, right? I'm gonna ask for Anthony. What's that?
Like
Anthony? Yeah.
answer. So 22x plus 484 equals to x plus 20 squared.
22x plus 22 times 22, right? Equals to x plus 20 perfect square. Yeah? Yeah, I see Matthew already. Yeah, it's pretty much everyone has the correct answer. Yes. With all of this, what can I do? I just have to solve it, right? Find out what's the value of x. X will be minus 9 plus under root 165. So one is going to have 1, you're going to have m, the other one is going to have n. So what is m, what is n? So m, and this is your m, this is your n. That's it, right? Adding them together, you get what you need. You see? It's like so easy, right? So this problem is question number 13, but you're not using something too crazy, right? You're just basically using the major arc and the minor arc. Well, the most important thing is you need to do a construction. This is a little bit challenging to find out such a graph. And taking from there, you just directly use the Ptolemy theorem, and then you'll be able to find out a solution. I think generally speaking, it's a fairly easy problem, but as long as you know the hang of it, right, you'll be able to do it. So this is like a quick problem. I want to say, you see, in the same circle, reach arc is longer, reach arc is bigger, reach arc is smaller. These are considered to be very basic stuff, right? So we always give the concepts and problem one after another, that you can utilize it, try to do your thing. Moving forward, let's continue our properties, right? We were actually talking about this. So same chord, same length. Another quick thing I think everyone knows that is, well, let's continue, right? Our property, angles of a circle theorems. We just talked about the arcs, right? The chord of a circle theorem. Now let's talk something about the angle of a circle theorem. So let's do a quick summary. I just want to summarize everything together, then you guys can basically reference that later. One thing we just talked about it, right? If we have a center angle, I have a inscribed angle, they're all facing for the same arc. This is theta, this is phi. We know phi is actually theta over 2. Yeah, this is what we just talked about it. Just want to put it here one more time. Help you guys to make everything together. Second is, if in a circle, I have an arc, AB is arc, AB is chord, I have a chord, and AB is diameter. Not any chord, it's a special chord diameter. So as long as AB is diameter, this is always 90 degrees, right? Angle C will be 90 degrees. So the diameter faced inscribe the circle. The diameter faced inscribe the circle is always 90 degrees. And also this is necessary and sufficient condition. If you have a chord facing a inscribed circle 90 degrees, this chord is going to be a diameter. Right? Everyone knows that? And the next one is the most important. I want you guys to remember. I have a circle. This time, I have a tangent line. A tangent line is facing the circle. Okay? And then from here, I'm gonna make a chord here, here. This is the famous tangent chord theorem. What is that? An angle included by a tangent line and the chord of a circle. You see, my angle theta. My angle theta is an angle included by a tangent line and a chord of my circle, right? So this angle will be the same measurement to any inscribed circle facing the same chord. I'm going to repeat it. An angle inscribed by a tangent line and the chord of the circle. My chord, I'm going to use the color maybe green. Okay, it's the same in measurement to any inscribed circle which is facing the same chord. So angle theta equals to angle phi. Do you guys know this? Let's have a quick survey. I like to understand where you stand, then I'll be able to adjust all the following lectures. Do you guys heard about it? Yes or no? Can I have some survey? Can I have some
No.
feedbacks? Huh?
No.
No? It's the first time? Okay, okay. It's good to know. Yeah. So remember this. This is the famous tangent chord theorem. An angle inscribed by, what should I say? Like an angle created by a tangent line and the chord of the circle is actually the same measurement to any inscribed circle facing the same chord. Facing the same chord. Okay? So far, so good. If we are good, trust me, this is such an easy property, but we're going to use this easy property. We're going to find a lot of interesting problems. So let's give you one sample problem. You can have a look at it. We already talked about it like American Amy problem. Let's go for a Canadian problem. Okay? Let's go for a Euclid problem. Number 1, number 2. There we go. Yep, I'm going to put it here. There you go. Let's look at an Amy problem. Let's look at a Euclid problem. This is a problem that comes from 2017 Euclid. Euclid is our Canadian problem, right? And question number 8. A part. Euclid has 10 problems. This is the last 3 problems, right? Euclid number 8, A part. So this problem says, in the diagram, line segment AC, DF, they are tangent to the circle at B and E, okay? Respectively. Also, AF intersects the circle at P and R, okay? And intersects as B at Q, as shown if CAF, I'm going to highlight it, equals to 35 degrees, okay? DAF, DFA, 30 degrees. And FPE, 25 degrees. Okay? With all of this, the question asks you, what is the measurement for PEQ? What is the measurement for PEQ? I'm going to give it a name PEQ. I'm going to say theta. Okay. I have 2 tangents, right? AC, DF, they're both tangents. You cut the circle into DF, BF, those 2 tangent foots. And then I give you a bunch of angles. With all of this, I want you to determine what is the measurement for my blue angle C. Think about it. How can I do such a problem? I can give you a hint. As long as you see tangent and the chord, you have tangent, you have chord, and then the question asks you to calculate angle, right? Normally, you have to use the tangent chord theorem. Two things. First, you see tangent. Second, you see the question asks you to calculate angles. Most likely, you're going to use the tangent chord theorem. I'll give you maybe 2 minutes. Think about it. How can I create those tangent chord thing, right? And then we'll be able to make it work. 2 minutes. Think about it. If you have any ideas, post it into the group chat, and we can always have some discussion about it. Right? I like to see your thinking process. I'm not really showing you the answer because I have the solution. Let's read it for you. No, I like to guide you for the thinking process, step by step, how to do the problem. How can we do such a problem? The question asks you to determine the theta, right? Theta, well, theta is not a tangent chord angle, right? Because our tangent chord angle is more like this. An angle which is included by a tangent and also a chord. But even though theta is not a tangent chord angle, theta is kind of like an inscribed angle. Does it make sense? Can I find a chord that is actually facing theta? You see, I have a
BP.
okay, who said that? Yeah,
BP.
is that right? Yeah, I think that's very brilliant observation. if I connect BP, I am going to be able to find a tangent chord angle. This ABP is definitely equals to angle theta. Does it make sense? Because this is actually facing the same chord. All right. Okay, I have two tangents, right? One tangent is actually my AC. I'm going to use the color highlighted one more time. Yeah. This is my first tangent, AC. I use it and then figure out tangent chord, that is theta. But don't forget, I have another tangent, DF. For this DF, do I have a angle, a tangent chord angle? Is there anything I can do from that to make it work? Can I do exactly the same thing? I find a tangent chord angle and taking from there, figure out a tangent, I figure out another angle or something.
ER.
R, do we have R here? Oh, ER, yes. ER, okay. Well, can we have something easier? Okay, just without having any auxiliary lines. Do we already have something right in this graph that you can see there's a tangent chord angle? Think about it. I think there's an angle already there, and that angle is very close to theta as well. Who can tell me? Can I focus on this angle? Is this like a tangent chord angle? The green one. It is, right? The green one is a tangent chord angle. So for this tangent chord angle, who can tell me what's the value for this green angle? Can I calculate it? Can I just calculate this green angle? Well, this green angle is not so difficult to calculate. Can I check for this angle? From this angle, can I calculate the value for the green angle? Phi, I'll give it a name, phi.
$65.
Is it right? Yes. Phi equals to what? 25 plus 30, right? Because phi is an exterior angle. Exterior angles equals to the what should I say, non-adjacent two angles sum, right? Two interior angles sum. That is going to be 55. That's brilliant. As long as this is 55, what is this? What is this?
55.
55 as well, right? Because this is the tangent chord angle, right? They're facing the same chord. Now, I think I only have one variable. I need to have an equation, right? As long as I got an equation, my work is done. How can I find my one equation? If I find one triangle, this triangle has three angles. Adding them together, it's going to be 90 degrees. It's going to be 180 degrees. That's basically what we're going to do, right? The $1 million question is, can you find me a triangle? A triangle and create a angle 1 plus angle 2 plus angle 3 equals to 180 degrees equation. And that equation only has a theta, then your work is done. So time for you guys. Think about it. How can I find such an angle? How can I find such a triangle and just to do the work? You need to think about it, right? And then we can have some discussion all together. I like you guys to think, right? Don't be too shy or, try to. I like to see how to think. The thinking process is very extreme. It's very important. Yeah, I see Toki already has the correct answer. What about the other students? Please all get involved into our discussion. We'll be able to see how we're going to do this. Think about it. It's our first lecture. I think some of the students are a little bit shy. Norris, try to get our hands dirty. We can have some discussion though together. Okay, I'll be asking for Toki. What do you think for such a problem?
I think we can got an angle. The angle BPQ is equal to 35 at theta.
This guy is theta plus 35, right?
Yeah.
Okay, what else?
And All of them are in the same triangle and equal to 180.
Exactly. Right? Look at that, right? Toki actually find out the triangle BP. In this BP triangle, you already have this. I'm going to highlight it here. You already have this 55 degrees. This is theta. This is 25, but you just do not know this. But this part, no worries, because this part equals to 35 plus theta. It's here, right? This is the exterior angle from that guy. So that being said, you can have in triangle BPE, it's going to be 55 degrees plus theta plus 25 degrees plus theta plus 35 degrees equals to 180. Right? Because all of this, theta equals to 32.5 degrees. You see? This is also Euclid problem. It's question number 8, the last 3 problems, but you're not using anything too flowery. You just use the basic definition, and then you will be able to solve the problem. Easy peasy, right? I think this is very understandable process. Nothing too complicated. So far, so good. Are we all on the same page? You see, as long as the question give you a tangent and then give you a chord, most likely you're going to use the tangent chord theory. Okay? So far, so good. Try to remember this. If all good, let's continue. See, we finished the first one, this chord of a circle theorem. Second was the angle of a chord theorem. And the third one, let's continue. Third one, we're going to talk about the points and the circle. The points and the circle. It's pretty much the position. This is something quite understandable. I'm just going to do it fairly quick. I have a circle. This is O, right? I have point A. So OA greater than R means the circle, the point is outside the circle, right? OA equals to R, the point is on the circle. OA lesser than R is actually inside the circle. This is something so easy, right? Nothing really complicated. I think you guys learned that from your elementary school, from your day school, like whatever. This is actually using a point to represent, the relationship. The point is outside the circle, on the circle, or inside the circle. And the parameter that we use is actually OA. The distance between the circle center and the A point. Actually, there's another way. Try to use angle. We can still use angle to represent the relationship about A as outside, inside, or on the circle. How can we use angle? I'm going to tell you the second way. Same thing. Okay, I'm going to go to the second graph. Here. And then let's say I have an angle. Angle P is here. So I have a chord. Okay, I'm going to give you something like this. Here. Here. And yep. You see? I have an angle. I have an AP. Oops. This is A. This is B. This is P. Okay? And taken from there, I have a alpha. And this is my angle P. So basically, I have a point, which might be outside, it might be inside, let's be on a circle. And also, I find an inscribed circle. I have an inscribed angle. They're actually facing the same chord. So inscribe the angle alpha, okay, facing AB chord. Okay, inscribe the angle alpha facing AB chord. Now, if P is outside my circle, angle P must be lesser than angle alpha. If P is on the circle, angle P is equal to alpha. If P is inside a circle, angle P must be greater than alpha. Can you guys follow me on that part? Do you guys follow me on this part?
Yeah.
You see? So we have two ways to represent the relationship for a point P. This way is what you learn from your day school. OA greater, equal, or lesser. Actually, you can still use angle to represent the relationship, the position of angle P, of a point P. So P lesser, greater, or equal to alpha will give you the relative relationship between P and the entire circle. Try to remember there are two ways, not only using OP, the distance, but also use angle as well. Okay, this is our number 4. This is our number 3. Let's go to a number 4. The number 4 is extremely important. Tangent of a circle. Tangent of a circle. So let's try to do the same thing. Have a circle. And I have a point P, which is outside the circle. You make 2 tangents, right? You can only make 2, right? This is P, this is A, this is B. So first thing, from P, there's only 2 tangents, right? From P, a point which is outside the circle, there's only one. There's only 2 tangents. If P is on the circle, there's only 1 tangent, right? Second, of course, you know AP is the same as BP, right? Third thing is, if I do a connection, let's go to red, connection. If I do a connection, OA, OB, OA is perpendicular to AP, OB is perpendicular to BP. This is something quite understandable, right? Nothing really complicated. Okay, so this is the basic stuff when you're talking about a point to a circle, right? A point outside a circle, you can make 2 tangents. The tangents are the same. And then if you do a connection, the 2 radius will be perpendicular to these 2 tangents. So that being said, I have my first conditional react. In our lecture, we're going to talk about many conditional react. It means that as long as you see such a problem, you're going to do such a thing immediately. No need to think about anything. Just do a conditional react, do it right away. My first conditional react will be, as long as you see tangent and circle, automatically you want to connect circle center and tangent foot. Because as long as you do the connection, you will automatically generate a perpendicular. Does it make sense? This is something quite understandable. Quite easy. Trust me, you're going to use that to solve a lot of complicated problems. Even though they look easy, but there's a lot of applications for that. Okay? As long as you see a tangent and a circle, try to do a connection between the tangent foot and the circle center, and you're going to generate a perpendicular line right away. Okay? So this is talking about a circle and a point. Then what about you have 2 circles, right? 2 circles, they can also tangent to each other. They can be interior tangent, they can be exterior tangent. But let's focus on the exterior one. Okay, I have two circles, they're tangent to each other. As long as you say this, I have another conditional react. What I need to do for this, there are several things you can do. First, connect circle centers. Connect circle centers. Second, make interior common tangent line. I'm going to do this one by one. First one, I'm going to do a connection between two circle centers. This is my first circle center. Oh, oops. This is my first circle center. This is my second circle center. Do a connection between my circle centers. As long as you connect the circle centers, you're going to find out your circle center and the interior tangent line, they will be perpendicular to each other, right? So it's going to be this. Let's give a name. A, B, maybe this is L, right? AB will be perpendicular to L. The distance, or what should I say? Like the connection between two circle centers, this kind of like a segment, is perpendicular to your exterior, to your interior tangent line. Okay? Well, the second one, the third one is actually more important. Make a exterior common tangent line. Exterior common tangent line. What is my exterior common tangent line? It's going to be something more like this. Try to find a good angle. Okay, this is my exterior common tangent line. Okay, from there, you want to create a very interesting triangle. Create an important triangle. What was that? Let's have a quick look at it. I'm going to do the following stuff. Use color maybe blue. I'm going to do a connection between the circle center to the tangent foot. And this is what I talk about, right? Whenever you see a line, this is here. Whenever I see a line, here, this is actually here, right? You see a tangent line, tangent to a circle. I always do a connection between the circle center and the tangent foot. Now I did a connection between the circle center and the big, like the big circle center and the tangent foot. And then I do the same thing. Small circle center and tangent foot. Now I'm going to do a perpendicular line from the small circle center, radius, like from the small circle center to one of the radius of the big circle center. We'll do something like this. Okay, I'm going to name this is, I don't know, C. This is C, this is D, okay? Now let's have a quick look at it because this is like a magic triangle. Let's have a quick look at it. In this magic triangle, let's see. Because if this is big R, this is small r, right? This is small r, this would be the big R. So this is small r, this is the big R minus small r. Is that right? This is like a easy peasy stuff. Everyone knows that. So far, so good? Okay. As long as you have this in this gray triangle, if this is 90 degrees, this is big R plus small r, this is big R minus small r. So therefore, what's the value for this? Who can tell me? Get your hands dirty, do some calculation. Who can tell me what's the value for this? Do a calculation, let me know what's the value. Who can tell me? How can I do this? No one knows?
The square root of r plus r squared minus r squared.
And what's the value for that?
I think root 2r.
2 under root big R small r. Is it right? This is a quick calculation. This square minus this square and under root, right? This is what? 2RR minus 2RR. So therefore, it's going to be 2 under root RR. Does it make sense? Yes or no?
Yeah.
So trust me, as long as you have this is 2 under root RR, and this is also 2 under root RR, right? So you will be able to determine the length of the common tangent segment, right? This is one tangent foot, this is one tangent foot, and then you would be able to find, okay, the length of your tangent segment, right? Because common tangent is a line. Line has no length, right? But you can cut it into a segment. And that being said, you will be able to get the segment of that common tangent line. So far, so good, right? I think this is something quite understandable. Okay, so if all good, let's continue. Let's continue. Okay. All right, now I understand what is the common tangent line, how to do the conditional react to do it. I think another very important part I want to do the summary is that, I think it's number 5, right? Let's try to determine something about a triangle and a circle. We're going to discuss some very important thing, a triangle and a circle. We know that a triangle must have a inscribed circle and a circumcircle, right? Always, always, always. So is there any special relationship between all of these inscribed circles or the circumcircles? Let's have a quick look at it. So I have a triangle, I have a circle. Then I'm gonna create a triangle. Okay, so this is my inscribed circle, right? So my triangle, let me give a name. A, B, C. Okay, so this is my inscribed circle. This is R, 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 right? So my first important thing is that the area of my triangle ABC is actually R times P, where P is half of the perimeter of my triangle. That one, does it make sense to you or not? Yes or no? Can I have some feedbacks?
What's S tri
Oh, S means like the area. I think I'll use the way that you like to see. You like to see this, right? The area. Does it make sense to you?
Can you explain why it's R times P?
Yeah. Why? Y is A, B, C, right? Why? R is the radius of the inscribed circle. P is the half of the perimeter of this triangle. Why? Why that one works? I'm going to give the explanation to you. Let me try to break it into 3 little parts. I'm going to give the different colors. Maybe this is blue. This is red. And this is green. Blue, red, and green. Okay. Okay, so my area, ABC's area, will be break it into the area of blue, area of red, area of green. Does it make sense? Okay, let's do this one by one. What's the area of blue? Is variable is a triangle is 1 over 2 r times a, right? R is the height, and C, I'm sorry, C. R is the height, C is the bottom. Because this is inscribed the circle, these are all tangent to each other. Is it right? All tangent to each other. So 1 over 2 r times C. 1 over 2 r times the red one is what? B. And the green one is what? R times A. So my triangle ABC's area will be 1 over 2 R A plus B plus C. So ABC will be equals to R A plus B plus C. And this, I give a name P. So R times P, where P equals to, does it make sense to you? Yes or no? You guys follow me?
Yeah. Thank you.
Right? This is understandable. So actually, this is a very important way for you to determine the radius of the inscribed circle. If I have an inscribed circle, how can I determine the radius of the inscribed circle? This is the way. R will be equals to ABC's area, A plus B plus C divided by 2. Okay, I want you to remember this. This is how you can determine a given triangle's inscribed circles, the radius. This is the way how you can do the calculation. Okay, this is more for generic, any kind of triangles, right? Triangle like acute, obtuse, right? You do whatever you like. And especially for right triangle, I have an even easier solution for you. For a right triangle, if I have a inscribed circle, I'm just gonna write it like this. Okay. If this is my A, B, C, right? So this is my A, this is my B, this is my C, R. If triangle ABC is a right triangle, in this, of course, you're going to do the same thing. It doesn't matter. You can do this. Okay. According to what we need, R can be equals to what? Area over A plus B plus C. Area is 1/2 A times B. 1/2 A plus B plus C, right? You can simplify AB, A plus B plus C. This is one way. Definitely, because this is good for all the triangles, it's also good for right triangle. But for right triangle, there's another way to make it work. A plus B minus C divided by 2. There are two ways to determine a right triangle's inscribed circle's radius. Okay, two ways to do it. One is using the traditional way. The other way is use the second way. So actually a quick, it's not an assignment, it's kind of like a homework, right? Because we have our assignment. I have a quick question for you guys is why you have two expressions? This is more like a homework for you guys. Why? Normal triangle, you just basically go for the first one, you're good. But for the right triangle, why you have another expression and how you can prove it? From the first one, how you can prove the second. This is more like assignment for you guys. You can think about it. Okay? You can think about it. So far, so good? Okay? So this is like the triangle and the circle. We talk about how to determine the inscribed circle's radius. Then what about the circumcircle, the outside circle's radius? Is there a way to do the calculation? Yes, same thing. Say you have a circle. This time is circumcircle, right? So ABC is actually inside. I'm going to change the color to black, maybe to blue. Here, here, here. Okay. I have a triangle ABC. And this is my circumcircle, right? So this is A, this is B, this is C. And this is my R. Do you know how to determine the circumcircle's radius for a given triangle? Do you guys know that? Do you guys know that? Maybe not. Okay, no problem. I'm going to give you the answer. So the circumcircle's radius is actually equals to ABC times 4S. Or maybe I'm going to use the way that you like to see is ABC's area. ABC's area times 4 as that's the denominator, and the numerator is ABC. 3 sizes, multiply them together. How can I deal with that? How can I deal with that? Who can tell me? Do you guys know this? Can I ask you for some feedbacks? These are very basic, very very important concepts that you need to know in order to go to AMC 12. This is advanced lectures, right? We're targeted as grade 12, AMC 12, Euclid, so on and so forth. So how are we going to do such a problem? Maybe 2 minutes, think about it. And you can give me some answers into the group chat. How can you do with such a problem? Well, in order to do this, I have to know that if you guys heard about some basic ways how to determine the area of a triangle. I'm going to use this. A, B, C, A, B, C. Let's say this is a theta. So my triangle ABC's area is going to be 1/2 A times C sine theta. Did you guys know that, right? Yes or no? Yes or no? You guys know this? Can I have some feedbacks?
Yes.
This is given, right? Okay. So we all know that this is like using the definition how to determine the area. And also we all know the sine law, right? B over sine theta equals to what? C over sine A. And the other one is, no, A over sine. Okay, give me a sec. B, okay, so I'm gonna use the easy one. B over sine B, A over sine A, C over sine C, right? Equals to 2R. This is the sine law, right? And the 2R is actually the radius of the circumcircle. So here, sine B is actually sine theta. So therefore, what is sine theta? Sine theta actually equals B over 2R sine theta, right? I'm gonna drag it to here. So just replace the value for sine theta. Then ABC will be equals to 1/2 A times C. Sine theta will be over 2R. So that will be what? ABC 4R. Now look at that. ABC equals to ABC's area equals to ABC over 4R. So R will be equals to ABC for ABC's area. Does it make sense to you? This is the way how you determine an area. Oh, wait, how you can determine the, what should I say, like the circumcircle's radius using the area and the three sizes of your triangle. Does it make sense to you guys? Yes or no? Can I have some feedbacks?
Yes.
You see, there are two ways for you to determine either the inscribed circle's area like radius or the circumcircle's radius. Either using one is here. This is determine the inscribed circle's radius, or here using the circumcircle's radius. Try to remember this. This is actually something very important. Sometimes it's going to help you to do a lot of very complicated problem. You can jump something very quick. Okay, you feel good? Let me give you an Amy problem. Trust me, if you understand what I'm doing here, this Amy problem could be very understandable. So that's an Amy problem coming from here. We're looking at a problem that comes from the date is 2011. Amy 2, question number 10. Okay, let's have a look at it, how we're going to do such a problem. So this problem says, okay, a circle with center O has a radius 25. Chord AB of length 30 and chord CD of length 14. You see, you need to highlight all those important information. Intersect at P point. The distance between the midpoints of these two chords is 12. Okay, the distance between the midpoint of these two chords is 12. The quantity OP square can be represented using M over Q, where M, Q are relative prime numbers. Find the number of M plus Q, M plus N divided by 1000. So like I said, this is like typical Amy way to ask you a question. But long story short, the question wants you to know, okay, what is the value for OP square? Okay, let's have a nice graph, right? Like I keep saying, all those like geometry problem, as long as you have a nice graph, you're almost right? You're halfway through. I have a chord, I have like a circle, this is AB, this is CD, I don't know, just want to give this, for instance, okay? So is that AB is here, one chord of length 30. The other one, there is CD. CD is out here. The length is 14. And the distance between the mid of these two. One here, one here, right? So let's say these are the two the midpoints. This is what? This is E. This is F. Okay, the distance between the two mid is actually, yeah, like the mid is what? 12. 12. So AB is 30. CD is 14. Radius 25. So these two chords actually intersect at P point. The question is asking, what is the length from, I'm going to highlight using the color green, about this guy, OP. How can I deal with such a problem? I have two chord. The two chord has two lengths, right? And then I'll be able to do a connection between the two chord. And the midpoints of these two chords connect them together is only 12, right? Like the what should I say? Like the measurement is 12. And then you want to see what's the value about OP squared. How can I deal with such a problem? How can I deal with such a problem? Two minutes, think about it. And then maybe we can share our ideas based on that. How can I deal with such a problem? Do you have any ideas? OP. OP is actually in the middle of not nowhere, right? How can I find out a way try to solve this? Normally speaking, whenever you want to determine the length of a segment, you want to put it into a triangle, right? And then maybe using your similar triangle, congruency, so on and so forth to make it work. But this time, I don't know where to put my OP, right? OP is actually in the middle of nowhere, right? So how can I make sure I can make it happen? I think before we jump to that, how to determine OP, we have two chord in this problem, right? And I even know the length of the chord. So there's another conditional react I like to share with you guys. Is that as long as you see a chord with length given in the problem, you can always determine the distance from the circle center to the chord. Okay, this is important stuff I want you guys to remember. As long as you have a chord with the length, then automatically you can determine the distance from the circle center to the chord, which is quite understandable, right? How can I do that? Now this is easy. I'm gonna use maybe color red, okay? So how can I determine the distance? I'm just going to do a connection. I'm just going to do a connection, right? As long as you connect the circle center to the mid of the chord, you will automatically have this is 90 degrees, this is 90 degrees, right? This is what I talked about in our lecture, the first thing. Because what? If you come to here, if you remember the first property, perpendicular bisection of your chord must pass through the circle center. AKA, if you do a connection between the circle center and the midpoint of the chord, you're going to generate a 90 degrees perpendicular line. Right? I think this is something very understandable. Okay, let's come to here. Let's come to here. Let's come to here. As long as I do that, I would be able to find out, okay, this is my distance 1. This is my distance 2. How can I determine D1? Who can tell me?
AO is 25.
Mhm.
And then you can use Pythagorean theorem. So square root of 25 squared minus 15 squared.
Is it right? So that be able, you want to determine the value. That's going to be 20. So D1 equals to 20. D2, you can do the same thing. That's going to be 24. One is 20, one is 24. Okay. This is 20. This is 24. Okay. This is 20. This is 24. And I know this is 12, right? The question tells you this is 12. I already know the 3 red lines. That's a circle. This is like a triangle, right? But the question asked me to determine what's the value for OP. So my $1,000,000 question is that how can I find out the relationship between OP and whatever is given by the current question? Previously, I was mentioned, if you want to determine OP, you want to probably put it into a triangle, so on and so forth. But if you want to put it into a triangle, let's say I want to give an example. Let's say you think about I put it into this black triangle, for instance. This black triangle, you know D1 already, but you really have no idea what's the value about DP, right? The black triangle is a right triangle. As long as you know 2 legs, you'll be able to determine OP. OP is the hypotenuse. But the $1,000,000 question is, I just calculate the value for D1, but I have no idea how to determine EP. Right? The question never said how the EP looks like. So it doesn't really work out so well if I put OP into a triangle black. Is there anything alternative I can do in order to properly put OP into a triangle or something or whatever in order to make it work? Who can tell me how can I deal with that? This is like one of the tricky part for this problem. Let's have a quick look at it about this triangle. This is like this red triangle. Of course, you know this is exactly, you have 3 sizes, right? 20, 24, 12. So what's the relationship between OP and this red triangle? Who can tell me? What's the relationship between OP and this red triangle? what's the relationship between my red triangle and this OP? I don't know if you guys know, look at this. This is 90 degrees. This is 90 degrees. If you know this, is there anything special for this 4 points? There are two 90 degrees, right? And if that's the case, is there anything special for this POF? Actually, PEOF, those 4 points, is going to be cyclic. Do you guys know that? Cyclic. PEOF is cyclic. Cyclic means they are actually staying on the same circle. Did you guys know this? So I'm going to ask you one more time. Maybe you do not really quite understand me.
Can you explain why they're cyclic?
Okay, so you don't really know that, right? So in the next lecture, we're going to give you more explanations. If you have a quadrilateral, PEOF, this is a quadrilateral, right? You know the 3 red lines, and then this is the OP. In the quadrilateral, if the opposite two angles are supplementary, aka angle E plus angle F equals to 180 degrees, so quadrilateral PEOF is cyclic. This is going to be a cyclic quadrilateral, aka they are actually on the same circle. If I draw out a circle, so this 4 points is going to be on the same circle. If you don't understand, we're going to talk about in our next lecture how to determine a quadrilateral as cyclic and what is the properties of the cyclic quadrilateral. Okay, because this is like advanced lecture. I thought you guys already know that, but it's okay. If you don't know, we can talk about it in our next lecture. If that's the case, I will be able to say OP is actually the diameter of the circumcircle of triangle EOF. Is that right? EOF is going to be a triangle. My circle, the yellow circle is going to be the circumcircle of this triangle. So my OP will be the diameter of the circumcircle of triangle EOF. If that's the case, trust me, this problem will be solved in 2 seconds. Because we just talk about what? R will be equals to ABC over 4, the area of triangle ABC. So within this triangle R will be what? OP divided by 2, right? OP is the diameter, OP divided by 2 will be R. Will equals to ABC. ABC, we already know the 3 sizes, right? This is 20, this is 24, this is 12. 20, 24, 12. Then 4, the area of my triangle EOF. How can I determine the area of my triangle EOF? How can I determine the area of my triangle EOF? Who can tell me? Do you guys know this? Use the color blue. How can I determine the area of my triangle EOF?
Ron's formula.
Is that right? Heron's formula, right? The other students, you know Heron's formula? The other students, you heard about the Heron's formula?
I don't remember it.
Heron's formula means if I have a triangle A, B, C, three sizes, the area of my triangle will be P minus A, P minus B, P minus C, and P is A plus B plus C divided by 2. Did you guys know this? Yes or no? This is the Heron's formula. You would be able to determine the area of a triangle using three sizes. You guys follow me?
Yeah.
This is understandable, right? Okay, so you would be able to determine the area of my triangle EOF because you already know the three sizes, 12, 20, 24. With all of this information, that one is going to be equals to P over 2. You do the calculation, you got a value for OP squared. It's going to be what you do for such a problem. I don't really do the calculation. I just want to show you guys the thinking process. All right, I think that's pretty much what I want to say for today's lecture. Today's lecture is a fairly easy lecture. We just talk about the basic concepts of the circle. We never go to some very complicated, very, flowery concepts. We have a lot to say, but this is just like the entry level, like the 101 lectures. Give you guys the definition for a circle, how to determine the circle's basic properties. So hopefully you guys have some rough idea about our lecture concept and the way how we organize. Just before I let you go, can I ask you guys to private chat with me which grade you are in? So can everyone, we do not have a lot, right? So can you tell me which grade are you in? Can you type it to me? All the students, please. Okay. If most of you guys are grade 11, means you're gonna go to AMC 12 and Euclid. So you have to go to advanced lectures. So yeah, this is good for you. If you have any questions about the concepts, so on and so forth we're talking about, let me know. And I'll be able to provide you some extra information, help you guys to catch up. So that's basically the kind of like, we have to go for the higher level, the more complicated problems to follow. So that's going to help you guys to expand your horizon and do a good job in the upcoming math competitions. All right, I think that's pretty much what I want to say today. You have any questions for me? Okay, I guess it's a no. I'm going to upload our assignment into our Google Classroom. You have 1 week to finish the assignment, and then we're going to ask you guys to explain the homework in the next lecture, and then we can take it from there. All right. Okay, thank you guys. And I'll see you guys for the next week. Bye, guys. Bye.
Thank you.
Have a good one.
Thank you.
Bye, sir.
Bye.